Hi guys. Sorry, it's been a while since I've posted any tutorials. I've been going through a bit of a rough patch lately, except the rough patch is every aspect of my entire life. And so I haven't had the energy to really do the things that bring me joy. And I'm just trying to take it easy and just rest as much as I can and just patiently wait for better days. But I've decided to try to muster up enough energy to do a tutorial today. So hopefully this goes well and I don't give up halfway through. So yeah, welcome back. All right, so a 25.0 kilogram child plays on a swing, having support ropes that are 2.20 meters long. Her brother pulls her back until the rope are 20 or 42 degrees from the vertical. And what kind of English is that? Okay. Her brother pulls her back until the ropes, 1 second, until the ropes are 42.0 degrees from the vertical and releases her from rest. A, what is her potential energy just as she is released compared with the potential energy at the bottom of the swing's motion? B, how fast will she be moving at the bottom? C, how much work does the tension in the ropes do as she swings from the initial position to the bottom of the motion? All right. Okay, so let's go ahead and understand this problem and sort of just draw it out. Okay, so this problem is actually really similar to our Tarzan and Jane problem. I don't know how far back it is. Just Google or YouTube it. You'll find it. Um, but similar-ish concept, but this is like a different, this is just another practice of that similar concept. Okay, so I'm going to draw like a swing set. It's going to be a rough sketch because I don't know how to draw a swing set, but okay. So let's say that's our swing. And this is like a side profile. Okay, I should write that down actually. So side profile, right? And we just have, let's say like this yellow dot right over here is just like the swing, okay? And we can draw a child on the swing as well. Draw her right there. She's just sitting on that swing. Okay, so what do we know? We know her mass is what? 25.0 kilograms, right? These ropes are 2.20 meters long, right? So L is equal to 2.20 meters. And her brother pulls her back until the ropes are 42 degrees from the vertical, right? So this is going to be theta, and theta is equal to 42.0 degrees. And he releases her from rest. Okay, so what's the potential energy as she's released compared with the potential energy at the bottom of the swing's motion? Okay, let's actually draw this again just to understand like part A of the question a little bit better. Okay, so like we said, swings right over here. And let's say this is like 42 again. I know that's not like the exact same angle as I drew over here, but we're just going to pretend they're both 42.0 degrees. All right, so, if this is a 2.20 long swing, let's say that this is sort of where she ends up, right? Okay, so this is going to be like point 1, right? As she's released, that's the first point. And then compared with the bottom of the swing, that's 2, right? All right. So now, how much work does the tension in the rope do as she swings from the initial position to the bottom? Oh, wait, sorry. No, that's part C. Okay. So, what is your potential energy as she's released compared with the potential energy at the bottom of the swing's motion? So, we're comparing the potential energy here to the potential energy here. Okay. So, a little recap on potential energy, right? So, let's talk a little bit about potential energy just because this question's a little bit tricky if we don't go into that topic first, okay? So, potential energy. Okay. So, potential energy, as we know, is one second, let me actually find the exact letter that we use because I know one second. I think it's U. I think we use U for potential energy. Okay, yeah. And the formula is mgh, right? So that's like the formula for potential energy, right? Where m is mass, right? That's gravity, gravitational constant, and then that is just our height, right? So potential energy is really interesting because of this right over here, right? So height, right? What is considered height when it comes to potential energy? This is tricky because we define, right? We define our reference. What does that mean? So, what that means is that let's say we want to know there's some, you know, person here on the cliff. Let's say this is our cliff, right? So, what's their potential energy, right? If you take this point right over here to be our reference, so if that's like our zero, then their potential energy is h, right? So how high above, the ground are they? 0 meters. So our h is going to be 0 over here, right? And then we have u is equal to 0, right? Because mgh, when h is 0, then that means u is equal to 0. So their potential energy is 0, right? However, let's say that this is some sort of like canyon, right? Not canyon, sorry. Let's say that there's like some ground right over here, okay? And let's say that we define this ground as our 0 point, right? Then h is equal to this this distance, right? And let's say that that's 10 meters, right? So then h is equal to 10 meters. And then therefore, right, our gravitational potential energy is equal to mg times 10, right? So really the point is that gravitational potential energy can change depending on our reference point. And so when we define our reference point, then we sort of also have this like variable gravitational potential energy. And so you might be asking, well, okay, if we get to define what our reference point is, then, like you could choose, someone could choose this point, someone could choose this point, someone could choose this point. And then aren't we going to end up with a bunch of different gravitational potential energies? And then what's the correct one for the problem that I'm solving? Well, okay, so that's an excellent question. I know I came up with it myself, but okay. So that's an excellent question because the question, the problem that you're given will sort of give you a hint, right? And so in this problem here specifically, right, it says, what is her potential energy compared with the potential energy at the bottom of the swing's motion? So we're comparing two potential energies, right? We're comparing, I'm going to write that in caps, comparing this potential energy and this potential energy, and therefore we can just look at the difference, right? All right, so let's get started. So how am I going to define our potential energy in this problem? So we don't actually know how high above the ground this swing is, right? We have no idea. I don't like that color actually in this setting. I want something a little bit more laid back, like a little bit more earthy. Okay, so this green, something not so intense. Okay, so we don't know if this is 1 meter or 2 meters or 10 meters, right? Like we're not given that information in the question, right? So what can we do? Well, we can actually define our reference point from somewhere else, right? So we can define our reference point from right over here, okay? So we can actually take this bottom part of this swing to be our u is equal to 0. Okay, sorry. That can be our, sorry, not u is equal to 0. That can be like our ground level, right? So this is our reference point, right? So I don't know why I wrote u there. Ignore that. But yeah, that's our reference point, okay? So the potential energy at the bottom of the swing's motion, we can say, so at 2, right? Actually, so first we're going to write down all of our givens, right? That's what we like to do first. So let's go ahead and write down all of our givens. So knowns. We have M, which is equal to 25.0 kilograms. And our ropes, which are length, 2.20 you know, meters. And we have this angle theta, which is 42.0 degrees. And yeah, that's what we have for our knowns, right? Okay. Sorry, give me a second. Okay, so yeah, we have our knowns. Okay, so now let's go to part A. Okay. Let's do a different color. Let's do blue. So part A, right? Part A, we know that 2, right off the bat, well, U is equal to mgh, right? And when h is 0, right, because we said the bottom of the swing is like our 0 point. So then that means at 2, mg0, and then that's just our potential energy is 0, right? So now what is our potential energy at 1, right? Okay, so we have to use a little bit of trig to figure this out. So our potential, oh, I really don't like that. Okay. So our potential energy is this, sorry, not potential energy. Our H is going to be this distance, like right over here, right? So how do we figure that out? Okay, so we know that this is L equals to 2.20 meters, right? And we know that this is also L is equal to 2.20 meters because, the rope's not really changing its length as it's swinging from one point to another, right? So now that we know that, we can use trig to find out what this distance is right over here. And how do we do that? So L, right? So this over here, cos 42 is equal to this distance right over here, right? So if we want to, let's just call this like x, right? So x is equal to 2.20 cos 42, and that is just 1.6349 meters, right? And then this whole length is 2.20 0, right? So then if we want to find out what this h is right over here, right, we just have to subtract, this from this. So h is equal to 2.20 cos 42, or sorry, 2.20 minus 2.20 cos 42. And what I get when I do that is 0.565 meters. And then UMGH is, 25 times 9.8 times 0.565 is equal to 138.44 joules, right? Is that right? Give me a second, I need to double check. Yeah, okay. See, so that makes sense. So compared with the potential energy at the bottom of the swing's motion, what's her potential energy just as she's released? So when we compare it to the bottom of the swing, where the bottom is 0, then our potential energy is 138.44 joules. Okay, awesome. So we got part A done. Now, what about part B? How fast will she be moving at the bottom of the swing's motion, right? So, all right. So let's also just like write down that known. Okay. So we're going to do U 138.44 joules. Okay. So B, we are looking at what's her speed at the bottom. Okay. So again, let's look at like the energies at these 2 points. So at 1, right, what types of energies do we have, right? Or what are we considering? So we have our potential, gravitational potential energy, right? So we have our U, right? And then we have our kinetic energy, right? Which is 0 because pulls her back and releases her from rest. So if she's being released from rest, that means that her initial speed is equal to 0, right? Okay, so let's look at 2. So 2, right, is right here, okay? At 2, she has, some gravitational potential energy, which is 0, right? Because we said that we're going to consider this point to be like 0, right? And then we have some kinetic energy, right? So we have to remember that the key is conservation of energy. Energy is conserved in this system, right? So all the energy from, point 1 is converted. So all the gravitational potential energy is converted to kinetic energy from U to K, which is gravitational potential to kinetic, right? And so if we want to figure out what our kinetic energy is, we can just equate these two to each other, right? Because the total energy at 1, right, is equal to the total energy at 2, okay? So the total energy at 1 is U, which is which is U, and then the total energy at 2 is K, right? So we're going to 1, 1, 2, 2. So we're going to do 1 and then 2. Okay. So K is just okay, actually U is 138.44, and that's equal to half of mv squared. And if we want to find out how fast she's going to be moving at the bottom, we just have to isolate for v, right? So 2 times 138.44 divided by m, which is 25. We're just going to square root that, and that's equal to v, right? And v is equal to 138. Well, okay, it's actually plus minus v, right? Oh, that's horrific. That is so gross. So plus minus, there we go. Okay, so 138.44 times 2 divided by 25. Square root that, and I'm getting v is equal to 3.328 meters per second, right? So that's our speed. That's our speed at the bottom. Okay, so now part C. Let's actually just write that down. V is equal to 3.328 meters per second, or I guess 3.33 with significant digits. Okay, cool. So part C now. Okay, so part C is, okay. Oh, I don't like that random circle. It's bothering me. Okay, so part C, and that is how much work does the tension in the ropes do as she swings from the initial position to the bottom of the motion? Okay, so what is work, right? Work is the dot product of force and displacement, right? So that's our dot product of these two. Okay, so let's actually do our force. So let's do a little diagram, okay? So again, this is our swing, okay? It's all in one color this time, so hopefully you're following along, right? And we want to take a look at which direction is the force of tension. So the force of tension is in, this direction, right? It's like what's it called? It's parallel to the direction of the rope, right? So, and it's anti-parallel to the force of no, it's not. No, that's not the right word. Okay, so yeah, it's this direction. It's parallel to the force of the rope, right? Um, all right. And so just to kind of illustrate that a little bit better, as we kind of, swing her around, no matter where the swing is, tension is always going to be, it's always going to be parallel to the rope, right? It's always going to be this direction, this direction, this direction. That's tension, right? Now, what about this displacement, right? So this displacement is always going to be perpendicular to the rope, right? when we're in like a circle, right? Think of this from like a bird's eye view, right? Um, and essentially like, a swing is like an arc of a circle. So that's why I'm using a circle. Okay. So the displacement, right? So like when the swing, even though like the force of tension is this way, the swing, it's always going to be like perpendicular to this force of tension, right? That's the displacement. The displacement is always going to be perpendicular. It's going to be like forward, 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 right? So, and if you want to learn more about that, I think I have like a circular motion video, so that's probably a good one to check, but I'm not going to go into details, but like basically you get the point, right? So tension and displacement are like 90 degrees from each other, right? And so what do we know about dot product of like two like vectors that are 90 degrees from each other? We know that it's zero. So because this, the direction of force is perpendicular to the displacement, that means that the work done by tension is zero. Zero. So work done by tension is zero. All right. So that's our solution. Hopefully this was helpful, and um, hopefully I have enough energy to do some more tutorials. But meanwhile, please don't forget to like and subscribe. And I hope this was helpful, and see you next time.